Hi guys. Today we'll be talking about parent strain theory and a little bit about primary and secondary bone healing. Before that, let's talk a little bit about why bone remodels. So bone remodeling is bone is a in a state of constant turnover all the time, where bone is being resorbed and bone is being deposited. Now, why is this important? This is important because as we go about in our day-to-day lives, when we run, when we do activities, sometimes there's small micro traumas to the bone or micro fractures which are constantly repaired. So when bone is being remodeled, these micro fractures are constantly being repaired and we won't feel it and we won't know anything about it. Also, suppose we change our activities, we start doing some activity, our bone will remodel according to the mechanical stress placed on it. Suppose we are doing something that places a little more extra stress on the tibia will grow to become thicker, and maybe we are placing more pressure on the inner side of the tibia, so the inner side of the tibia will hypertrophy. This is just a very rough example of how bone remodels according to the mechanical stress, and it change the shape and the size and the structure of the bone accordingly. And also, bone is a source of calcium and phosphate for the body, about 90%. So, again, calcium is constantly put out by the bone when the body requires it. And this is primarily dictated by the parathyroid hormone. So, coming to the discussion at hand, we'll talk a little bit about primary healing or direct fracture healing. This is the type of fracture healing that occurs without any callus formation, no callus formation. Now, why is that? So we know that in order for primary or direct healing to occur, we need a rigid fixation with good compression. So in case of a humerus shaft transverse fracture, is for forearm radius and ulnar transverse shaft fractures, what we do is we place a plate, a compression plate, and then we compress. We make sure the ends of the bone are in contact with each other and at a certain compression. Now, what happens when this happens is it convinces our body or makes our body think that, oh, okay, this is not exactly a fracture, it's just a micro trauma and there's a crack in the bone ends are in contact. So, what the body will think is, and it's also rigidly fixed, so the body will think is it's not fractured, we'll just remodel it. That is the reasoning behind how this works. So, what it will not go to the standard phases of fracture healing. Now, what are the standard phases of fracture healing? They are the inflammatory phase where a hematoma is formed. After hematoma, granulation tissue is formed. Then there's a soft callus, which is a fibrocartilaginous callus. And then after soft callus, a hard callus, when a little bit of calcium is deposited in the callus. And then a woven bone is formed. And finally, after remodeling, a lamellar bone is formed. And the remodeling process goes on for a long time, about many years. And then eventually, the bone is wholly formed. So, in primary direct fracture healing, all this is skipped. It directly remodeling occurs. And how does this occur? So, when the bone ends are in contact, there's little bit of tissue comes which is grown in between, and the cutting cones use that tissue to cross over to the opposite side. So, cutting cone from one side will traverse across the fracture site, and initially it will resorb the bone, and then in the front part of the cutting cone there are osteoclasts, and in the middle part there's osteoblasts. So initially the bone is resorbed and then it's deposited. So if a cutting cone goes through a fracture multiple times, and many cutting cones do the same thing, the fracture gap is eventually bridged with bone, and osteons are laid down directly. There is no cartilage formation. This is intramembranous ossification. And for that, the prerequisite is a rigid fixation with anatomic reduction and hopefully a good compression. Okay, now that's primary healing. Secondary healing. Secondary or indirect bone healing occurs when there is relative stability. Rigid fixation and absolute stability, primary healing. Relative stability is indirect or secondary bone healing. This occurs with callus formation, and usually the callus which forms outside also. You would have seen it in an X-ray, and this occurs initially with cartilage formation, and the cartilage is eventually converted to bone, and it goes through these stages as I spoke about: hematoma, granulation tissue, soft callus, hard callus, and woven bone, lamellar bone, and remodeling. Okay, so now As you can see here, this is an example of a compression plating. And in this kind of compression plating, what would have happened is this you see the bone ends are in contact and there's compression across the fracture site. So you can see there's no excess callus formation occurring outside. The bone is directly formed, and this is an example of primary healing. Whereas when we nail, there is relative stability. Here there's absolute stability. When we nail, there's relative stability, and you can see there's excessive callus formation. A lot of callus is formed both anteriorly, posteriorly, medial, and laterally. And this occurs, and this is relative stability. So eventually, soft callus is formed, then hard callus, then bone, lamella bone, and eventually all this excess callus will be resorbed once the remodeling process is done. Eventually, the end result is the same, but the way it heals is different, basically. So, what is Perrin's strain theory? Perrin's strain theory states that the interfragmentary strain determines the type of tissue that is formed in the fracture gap. So, 10 to 100% strain results in the formation of fibrous tissue, 2 to 10% strain results in the formation of cartilage, and less than 2% strain across the fracture site leads to the formation of bone. Just remember these numbers. And he also stated that granulation tissue has a strain limit of 0.01 kp per mm square, cartilage has 1.5, and bone has 13. So the formula for strain is total change in length divided by the original length, or the total elongation divided by the original length. Same thing. So when we apply this formula, suppose the initial gap across the fracture site was L. Delta L is the strain placed across the fracture site. Delta L is the strain placed across the fracture site. So strain is nothing but delta L by L. Let's take, for example, 1 is the length, 1 centimeter. Okay. Delta L, let's say, is 2. Okay, we'll take 10 centimeter to make the math easier. L will be 10 centimeter. So delta L will be, if you want, so for 100% strain, delta L will have to be 10 centimeter again. So 10 by, if we apply the formula, 10 by 10 strain into 100, strain will be 100%. Okay. So there's another 100 here. So just remember that. So 10 by 10 into 100 will be 100% strain. And if there's 100% strain, what will happen? There will be fibrous tissue formation. There will not be any cartilage or any bone formed. Now, for example, let's take 1 centimeter is the delta L. So if we use the formula, 1 centimeter divided by 10 into 100, what do we get? We get 10%. So 10% strain across the fracture site, 2 to 10%, remember, cartilage is formed. This will be, so if there's around 10% strain on the fracture site, this will be a type of relative stability, not absolute, and there'll be callus formation and secondary bone healing will occur. Now let's take an example of 0.1 mm. So 1 centimeter is 10 mm. Okay, so 1 mm divided by 10 centimeter into 100. How much we get? We get 1%. Okay, so 1% strain. So as we know, when there's less than 2%, primary fracture healing or direct intramembranous ossification will occur, direct bone healing will occur. So if the strain is less than 2%, we get direct bone healing. Now, imagine there's another situation. So 5 is the initial gap across the fracture site. If there's an increase in length of 5 centimeters, remember. So if there's an increase in length of 5 centimeter, 5 by 5 into 100 will be 100%. There's 100% strain across the fracture site. So this will not heal. This will lead to fibrous tissue formation, eventually non-union, and will eventually lead to a pseudoarthrosis. For example, here, imagine between each of these fragments, there's already a 5 centimeter gap. And the total change in length across all these fragments is another 5 centimeters. So in between each fragment, there will be an increase in length of 1 centimeter. So the 100% strain across the entire bone across this entire fracture graph is distributed into 5 spaces. 1, 2, 3, 4, 5. So there'll only be a 20% strain across each of these fragments because it is distributed among 5 fragments. So what happens is the strain is lesser. So this will heal. I know the strain is still more than 10%, which is ideal for us. We want it to be less than 10%, but you get the idea. The strain, I'm just trying to explain the concept here. The strain is equally distributed, and this is why when there's a comminuted fracture, we bridge plate it. Bridge plating is not absolute stability. It's again a form of relative stability. So this is the principle behind why we bridge plate comminuted fractures, because the strain is distributed across each of the fragments. Okay. So this is an example of a pseudoarthrosis. A pseudoarthrosis forms when the strain is too much and the fixation is not stable enough. Okay. So the body is like, okay, the body adapts to how much movement there is across the fracture site. So imagine there's more movement across the fracture site. The body will not form bone there. It'll be like, okay, maybe this person requires movement across the fracture site, so we'll just form another joint there. And that's how a pseudoarthrosis ends up being formed. Okay. So again, this is a diagram showing the same thing. As we move towards rigid fixation, primary healing occurs. And as we go towards more loose fixation, casting, static splinting, K-wiring and all, secondary healing occurs. And this is an example of something we should absolutely not do. So when we rigidly fix something, we want the bone ends to be in contact, number one, and we want compression across the fracture site. So if we rigidly fix something and the bone ends are not in contact and there's a fracture gap, primary healing also cannot occur because the bone ends are not in contact, so the cutting cones won't be able to migrate across. And also, secondly, secondary healing will not occur because there's not enough movement across the fracture site. It's too rigidly fixed. So we're doing a disservice to the patient by fixing it like this. So if we fix rigidly, we should make sure there's compression and bone contact. That'll be all. Thank you.